The discussion for this session is, first, we want to see a code together about fine-tuning BERT. We won't go into details of fine-tuning because we would have a session on it specifically later this week. But yeah, so you can go to this link if you want. I'll just show it. For people who are on Zoom, you can just also go to the link if you want. And yeah, let's go and see a quick code that how you can fine-tune a BERT for a simple task. And then we will also see some details. So let's quickly open this link. What's this? No. Sorry. Share. Okay. I hope you can see it. You can see the screen on Zoom, the Safari browser. Okay. So you this is simple code for fine-tuning BERT. I will go over it. You can usually just get a code that just works and put it and just change it for that to work for you. So you first install a lot of packages. I mean, these are the standard thing, PyTorch. They don't matter a lot. There's a transformers package that helps you a lot. This is from Hugging Face. And there's also a datasets package that helps you in downloading datasets that are available on the Hugging Face Hub. Instead of downloading the CSV yourself and then needing to load it in like pandas, you can just use the datasets library to pull datasets that have been shared by other users, which is a very, very cool dataset. I think Eric is actually who wants to provide the lecture on, I think, Friday or Wednesday, Thursday, somewhere like that, about fine-tuning, and he would also cover Hugging Face in details. But apart from that, yeah, there's a certain package that we also use for pooling datasets that other people have used. As you can see here, it's called the Hugging Face Hub. So it's something like GitHub, but for models and datasets. So to use it, you first need to have a Hugging Face account. You can just create it on Hugging Face. It is usually needed for downloading some models. I don't think for downloading open models you need to log in. I don't think, but some models need you to accept like some terms and conditions before you're downloading. So you usually do that on the website, and then you can log in with your token that you can get from your profile, which is very obvious. Okay, this is not any kind of deep learning code, but here. So this is the dataset library that we talked about. It's a very nice, very good interface for downloading datasets. So when you go to Hugging Face, here is Hugging Face. Where you go here, there's a datasets tab here on top. You can click, and these are a lot of datasets that you can see it's actually active, updated 2 hours ago, like 20 hours ago. So people are actively putting datasets here. You can find a lot from many different domains. You can check the modalities. There's also not only text datasets. This platform also works for vision, for audio, for image, and like for video. But here, okay, we want text. And then you can specify the size and like things like this. For example, this is a dataset and this is a dataset. Like these are ton of datasets, and each of them, when you click on them, you usually have a dataset card, which is a description of the dataset. You have a dataset viewer, which I'm not in the authorized list of the dataset, so I can see. But let's see a dataset that we can authorize. For example, the emotion one that we just talked about. Like this is the dataset. So there's a viewer, which is quite similar to this. You can see the distribution of length of the text of the entries, as well as the distribution of the class labels. You can see some classes are more represented than other classes. For example, this is joy. Like this is the emotion classification. Each sentence is joy or sadness, or okay, joy is 33%. Like sadness is 29, and some classes are very low, like surprise, love are lower. So yeah, this is and also it's a very nice way to see the data set and get a feeling of how it works, the text and the labels. And what else do we have here? We have also the files that you can download, the raw files if you want, the data here. And there's also you can, something like GitHub, you can provide pull requests or like you provide issues and things. So this is Hugging Face dataset. Whatever dataset you find here, for example, you want to solve a deep learning task, one of the first things you can do is to search Hugging Face for a dataset. You find some dataset, then you want to use it in your code. It's very simple. You just, from dataset, import load datasets, which is like the import sentence. You provide the dataset ID which is actually the ID that you can also copy from here. So there's a copy button, you just copy this. Usually the ID is with the username of the user as well. So the username of who uploaded the dataset slash the name of the dataset. And if there's no some datasets don't have the username because I think they're uploaded by Hugging Face itself, something like that. But anyways, when you put the dataset ID and then you call load dataset, it's very simple. It downloads it for the first time, then it caches it. So the next time it doesn't download it again. If the dataset is big, it just caches the dataset locally in some folder, and I think there's also some way to remove the cache if you want, but otherwise it keeps the dataset until sometime. For example, here you can see when I run this code, like they run this code, found cache dataset in this path, home Ubuntu or something like that. Yeah. Perfect. Then all datasets, most datasets, some of them are just a set of sentences, but many datasets are also have their own train test split done by the authors. So you don't need to do it yourself. Here you can see that they have the train test split themselves. It's very like they have already provided a train test split. You can just access to them raw data set of train, raw data set of test, and you can see like there are 10,000 train and 3,000 sentence in this banking data set. Okay, and okay here they are just picking a random example from the data set. As you can see, you just do the train. This is the training set, and then there's an array. So you can just pick one. This is a dictionary of text and label, as you can see here. So this is just loading the data set. As you can see, it's very simple to load data set and work with it if you use this Hugging Face library. So any question until now? I think it's fine. You can go over this easier stuff easy, faster. So this is the part that we want to load our model. So from transformers import auto tokenizer. What does it do? It infers the tokenizer type automatically. So there are some auto something in the transformer library that they automatically find the type of the model and the tokenizer. So it makes your job simpler. You just import auto tokenizer, then from pre-trained, and you give a model ID. This model ID is also from the Hugging Face hub. So it automatically downloads the model from Hugging Face, the files and everything, and also the tokenizer, because the tokenizer is also saved, the mapping is also saved. And by from pre-trained, you just load it from the hub. So the first time it downloads, and the second time you can easily use. Then they define the function for tokenizing each batch, which just calls the tokenizer. So this tokenizer is actually a callable function. If you call it with input, it tokenizes it and returns the output. Then you specify the type of padding. What they're doing here. You specify a type of padding. Here, the padding is that pad everything to the maximum length. So there are different types of padding. We won't go over the specific details here, but you can see the documentation. Sometimes they make some differences in the model, but they're not usually important. Also, the truncation is that if it is longer than the context size, what should it do? And finally, this is the type of sensor that it returns. I think you should type PT for PyTorch to return PyTorch sensors that we can work with. So it automatically also converts the data to sensor. Okay, here they rename the column label to label. I think they need to do this because the other code, like the Hugging Face code, the data set was called label, but the code of training is label, so you just rename the column, and then they tokenize it. They tokenize the data set by the map function. Map function in Python usually gets the list, applies a function on each entry of that list, right? So we just call the map function and pass the tokenized function. And we also want the batch version, and then after tokenizing, we don't need the text anymore. Because like yeah, I think they just remove that column. So yeah, this works. And now we have tokenized the data set. Now we want to fine tune our model. So first of all, before fine tuning, we need to load the model. So what do they do here? They import another library, auto model for sequence classification. This is actually similar to auto tokenizer. This is a class that can automatically infer the type of model you download from Hugging Face. You provide the model ID. Here they are using the uncased version. As I told, the uncased version is the same BERT, but trained with text that does not include capital letters. Everything is converted to lowercase area, I think. So yeah, if you can use this model, but remember that you should not pass text that has capital letter to it. It would work, I think, but it's not very useful because it is trained with another data that you are not putting it in. So anyway, they get all the labels like the name of the labels from the data set. And also they have a num of labels. They have a mapping of label to ID and ID to label so that they can later, when they want to show, okay, this sentence is from this class, they have a mapping between labels and IDs. And finally, okay, the important part here, they want to download the model here from Hugging Face. So they just use the function from pre-trained in this class, auto model for sequence classification. From pre-trained, load is from Hugging Face. They just provide the model ID, the number of labels, and the mappings. So that it can, because in the hub, the mapping is different, right? The mapping can have sometimes string mapping and we want integer mapping or vice versa. So we always provide the mapping to the model so that it knows. It's very obvious. Then here we want to, okay, go into the training process. But before that, we want to have a helper method for us to compute metrics. So here we are using the F1 accuracy. F1 accuracy is something like a balanced weight of accuracy, precision, and recall. I don't know if this has been covered, like the precision recall. Okay, I'll talk about it in the end of this session. So this is an accuracy, kind of accuracy metric. For now, assume that this is an accuracy metric. I will cover it in the end. And yeah, here they're just finding the predictions and like comparing the predictions with references. It's just a standard evaluation thing. We can, and also they're averaging weighted means weighted based on the class. Why is it important? Imagine you have a classification. 90% of text are from class sad and 10% are from class happy. And your model predicts every sentence as sad. Then your model has a 90% accuracy, but it's not good, right? Because it's just 90% accuracy because 90% of the data was sad. So you usually do weighted average. And this is actually a big thing. You sometimes see some papers claim high accuracy. I've actually seen them. And that's because just the data was imbalanced. If the data is imbalanced, the accuracy, you should pay attention to that because maybe high accuracy is just predicting one class. And that class is the majority, so the accuracy is 90%, but it's not a good model. You usually weight by the, like, do proportional to the size of each, to the number of count of each class in the training data. Yeah, usually do theories like this. And also there are some metrics. Maybe in the end of this session, I will go over them. So yeah. I thought maybe it was covered in the first week, but no, it doesn't matter. I will cover it. It's mostly for classification. I mean, for other types of loss, like regression loss or this kind, usually have mean square error, but for classification, this accuracy things sometimes matter. I'll go over it.
We have the two components of that. So F1 is the mean of precision and recall.
Yeah, I think kind of mean. Yeah. Yeah. And exactly. I mean, I'll cover the accuracy metrics in the end if you want. So yeah, no worries. But for now, imagine this is the kind of accuracy. So now this training part. So Hugging Face has provided some API to help a lot in training, and you can see there are a lot of parameters that you can change here. So okay, this is the remote repository that you can upload your model to. This is also a nice thing on Hugging Face. If you fine tune a model, you can upload your fine tuned model so that other people can use it without fine tuning again. So you can just provide an ID, and it will automatically upload your model in the end to Hugging Face. Imagine, given that you have logged in earlier. So you have a very big object called training arguments. In this object, you can configure every argument of the training, like everything, like all hyperparameters. What are the important things here? The batch size of training and evaluation. Hello. The batch size of training and evaluation, the learning rate, the standard things that you know. The output directory, like the standard thing where you should write the model, like to store the files. The number of epochs. I don't know BF16, what does it mean? But yeah, I think it's kind of precision thing, maybe float 6.
It's mixed precision. We had this on Friday.
Oh, okay. Yeah. I'll not go over the specific detail. I just want to, because I don't even know many of them. But yeah, you find the optimization and how many steps it should log, like the log and things like this. So you can read all of them. Most of them I usually just copy it and like change it whenever I need, because most of them doesn't matter a lot. Yeah, and push to hub is the one that I was just saying. You will also see it later in the fine-tuning session in details, that it would automatically push your fine-tuned model to the Hugging Face hub so that other people can use it. Yeah, and here it says that, for example, after every save of the model, upload it again to the hub. Then you just create a trainer object, which is from me. Yes, but okay. So you have your trainer object, you just pass the model, the arguments that we define, the training data, the testing data, and the function for computing that. Okay. Then you call trainer the train. And you can see some plots and fancy things. And yeah. And also, I mean, if you don't push to hop in the function, you can save. Oh, I mean, yeah, you can save the tokenizer, then create the model card that's was necessary uploading to the hub, and then call push to hub so that it pushes the last model to the hub. For inference, it's even simpler. Again, we'll cover this in the Friday, but you just call the function pipeline. You provide the task. Here is sentiment analysis. I think they call all classification tasks sentiment analysis, but it's the kind of text classification. You provide the model, which is the ID that you pushed because you want our model. The tokenizer, again, the same ID because you want to use the same tokenizer. And the device, I think, like GPU, CPU, and then provide a sample and just pass it to the classifier. And you can see this label with this probability or score. So it's very simple. Like this is how you usually fine-tune BERT model for text classification. You can just use the same code, just change the data set. If it's from Hugging Face, it's just changing the name of data set. But if it is your own data set, either you upload it to Hugging Face and then use the same code, or you can just replace the code that prepared the data set with your own, and you would have a BERT out of box, like fine-tuned to it, which is very like it has made things very simple, and it runs also pretty fast. By pretty fast, I mean I tried once using CPU, and I think fine-tuning BERT for one epoch on my CPU, not GPU, took maybe 3 hours or so, which is okay because full tuning of 110 million, I think it would take more time, I assume. And this is good without GPU.
Not QE or AG.
What do you mean?
I mean, if you are working for 3 hours to train one model.
Yeah, I just wanted to test. No one trained, I think, using CPU. Like everyone uses GPUs, which I think can train this model in 5 minutes or so. I just want to say, even without GPUs, like our older school CPUs, can fine tune it in a reasonable time and have a very good accuracy, like maybe 90% accuracy. With GPUs, I think 5-10 minutes. I don't think it would take more. We can test, but it depends on the GPU as well. But I think it would not take more. And also prediction is quite fast as well. So I don't think it more than half a second or so. You can easily do a prediction with one sentence. Just you call classifier and it will return you the prediction. And as you can see, it automatically maps it to the text because we have provided the mapping label to ID, ID to label. So it knows that, for example, label 1 from the model corresponds to this class, which makes it very nice if you want to like print it to the user and show it to the user. So yeah,
Does that
Yeah.
label mean something to you?
here,
Because at the beginning, I mean, in this example you showed us before, there were things like happy, sad.
yeah, this is a banking data set. The data set, I think, is about, let's just see the data set together. Because why do I scroll and it's like this?
Since because it's a right, like right on your left.
What about now? I hope now is better. I hope. So, okay. Banking 77. Let's see these data sets. Yeah, because this is another data set. So, oh yeah, you can see these are, I think, information asked about from a bank support, I think. I'm still waiting on my card is a card arrival class.
Okay, no,
Yeah. It's the code is not from emotion, but you can also use the same code for emotion. Yeah, I just picked that code. So yeah, card payment, transfer, transaction, like this is
Return code for my bank. Going to use this data set.
so here. I mean, here you can't respond. It's just for identifying. I think this data set maybe was used for knowing which person should the request go to. I think for that is very useful. I think if you want to have a system that there are humans in there, so computer is not answering, but you want to find the request of users corresponds to which employee. I think maybe this is very nice. So there are a lot of these. I think it's actually pretty old. Can we see when it was from? I don't know.
2003,
Where's that?
the very top, the right.
I missed the year. Then this is very old. 2020, actually. I think that's another code. Like it's not the year. Yeah, 2020. But still now it's considered old. So yeah. So yeah, it's considered old, but still you can see there are a lot of good data sets in Hugging Face. But in practice, I mean, many times we don't use data sets that are already there. We may have our own data sets in research specifically. Like if you are doing a certain research, you collect data sets also in a part of your research sometimes. For example, we in our lab, we work with students. We collect data from students and then we use them to train models sometimes. So it's not always the case that some data set is there, you can just use it. Also, part of the task is to preparing a good data set. But yeah, so this is the general, very basic approach to have a baseline model to just want to see. So any questions here? Or we can continue on the slides. Yeah. Exactly. So here, the BERT, in the banking data, the BERT was not trained with the banking data. BERT was trained on a very big corpus from the internet. I don't remember which source it was, but it's a very big corpus. Banking was very small. I think it was written here. It's just 1 megabyte. The banking data is just 1 megabyte. You can't train a good model from scratch with 1 megabyte. It's nothing. But the model actually works pretty great just by fine tuning on the 1 megabyte data. And that's the nice thing about transfer learning. Yeah. So it just fine tuned on this. Any questions? We can go. Perfect. Let's go. So, I mean, you saw the answer already, but one downside of BERT, we would talk about 2 downsides of BERT today. And for 2 of them, we would provide 2 solutions. One of them briefly, but one of them with more details. So one downside of BERT compared to maybe traditional model that used was that it's like many transform models, it needs a lot of memory. And also, even though I said inference time is low, it's more than traditional models. If you make your chatbot, as they say, for example, imagine the same domain, we want to see which request should go to which user in a banking app, which client should go to which employee of the bank. If we use a regular expression for that, very simple rule-based models, for example, you see, if you find the word card in the question, go to employee 10. If you find the word transaction, go to employee 11. If you use this, it's very fast, right? It's almost nothing, like maybe milliseconds. It would done in milliseconds. But a BERT model that does the prediction has still some inference time. It's nothing for a simple text, but also now that our GPUs are way stronger, it's also nothing. But back in the day, it was a problem when you wanted to do a prediction on a lot of text. For example, there's a whole document, and you want to do prediction for each label. Why is it useful for? Imagine you have a system that wants to see if your text is happy or sad or not. And you have trained your model on single sentences. So you should do the prediction on each sentence, all of the sentences in the document. For example, you have an email, which is 20 sentences, and you need to do the prediction on all of them. Either you need to do all of them in parallel, which means you need a lot of memory and like GPU and everything, or you need to do them sequentially, which takes a lot of time because it adds up over time. The user wants to exactly see at the moment when they are writing their email, they just see a happy or frown, a smile or frown icon while they are typing. They don't want to click a button and like wait 20 seconds until they receive such a button, right? So IEL people always wanted to reduce the inference time. By inference time, I mean the time needed to provide the predictions, and also reduce the memory needed for such models. Because a BERT is half a gigabyte. Okay, now it's nothing, but just some years ago, our smartphones were, I think the flagship iPhone was like 4 gigabytes or so, just some years ago. And this would take and also there are a lot of system stuff in there. So even half a gigabyte could have been a lot. I think now our smartphones have a lot more memory, but still these kind of problems are there. So models need a lot of memory and inference time. How to reduce? One way that people have done this in the past is quantization. What does it mean? Briefly, we don't go over into memory time reduction techniques a lot, but we will briefly cover them. In quantization, we show or represent the numbers with less precision. For example, we use a 16-bit float instead of 32. We use it in like we convert all numbers to a small how should I say, to a format that takes less memory. Like a float 16 is half the size of float 32 in memory, right? So if we convert all the weights of the model that are float numbers and 32 bits into 16-bit weights, the size of model would be 50% less. We have some information loss, certainly, because when you decrease the accuracy of representing a number, it's not very helpful. But sometimes the benefits of the less memory time can be worth the small performance hits. So you may think if this was successful or not. Actually, yes. So quantized models are not so worse than non-quantized models. But for BERT, it's not very important. Now it's more important for large language models that provide text generation. Maybe you have seen that sometimes when you want to download models to your device, these big large language models usually don't run on your device because they don't fit in your memory. Like if your memory of your laptop is 16 gigabytes, I think apart from a small llama, you can't run anything else, a good LLM. But you can run their quantized versions. So people are quantizing LLMs. They have some performance hits, a decrease in performance, but the benefits are usually more because there's less memory and time, less memory and less inference time. It can fit on your laptop. It can run locally. So these are all the benefits. While still they have maybe 80% of the performance of a full model that is running in the cloud. So it's also good. Imagining you are developing an assistant that you want it also to work offline, but you can't fit the model that you are using into your app because it should be run on the people's smartphones or smartwatches or like these kind of edge devices. You can do a quantized version, and whenever users are offline, you can use that model, and you can show them a text saying that if you want a more accurate response, please connect to the internet so that you can use the best models available. And then when you, for example, when you connect to the internet, the request can be sent to the cloud. This is something that sometimes people do. I think in recent models, also in large language models, they are doing this. So this is the idea of quantization. You can also convert to integers. So you can split the range of possible numbers into sub ranges and map each of them into a single integer. So somehow you are making it discrete. You are making float numbers discrete. This can be also done. This is a lot of information loss, but also a lot more saving in resources and time because computation with integers are way like faster than computation with floats. I think even sometimes people have converted to binary quantization, like everything to either 1 or 0, like very extreme quantization, and it still works to some extent. So sometimes we see some this kind of fancy stuff, but yeah, we don't usually do that. But we can quantize to a certain range and decrease the accuracy of the numbers or of the weights and biases in order to make less memory and less inference time, but still have quite the same performance. Any question here? Perfect. Another way that we'll also cover briefly today is knowledge distillation. What's that? Knowledge distillation, also a very famous model called distilled BERT, is a knowledge distilled version of BERT. But what does that mean? This is the idea that we train a smaller model called the student model to replicate or imitate how a bigger model behaves. What does that mean? When you train a BERT, you train it using the whole data on the internet. The idea was that we take the BERT, we make it smaller, like for example, instead of maybe 10 layers, we make it 8 layers, like a bit smaller. And then we train it not from the output in the internet, but from the output of the bigger BERT model, from all the probabilities and scores returned from the big BERT model. The model lost here is to imitate the larger model.
So you're taking the data set with the same distribution?
Yeah, we don't touch the data set again. So here, the goal is, I mean, you don't train on the data set again. So BERT was trained on masked language modeling, right? You mask some word and then you try to predict. Here, you use again the same, but instead of comparing with the true labels, you don't learn on the true labels. Rather, you just want to imitate what the larger model predicts. For example, if the larger model says the gap 80% enjoy, 20% attend, the smaller model should also be as close as possible to 80% enjoy, 20% attend for the missing word. We wanted to replicate the distribution of the larger BERT. What's the idea behind this? If you just trained a smaller model using the data set, it's not as helpful because usually you need a big model to capture stuff in text. But when you have already captured patterns in text, you can use the distribution of the big model to train a smaller model instead of the text. You just use the distribution of the bigger BERT model. I don't know if I've conveyed it in a good way or not. Yeah.
What's the data set you use? This is small. set?
No, you can use the same data, the same text. You can use the same text, but here you just imitate the bigger model. You don't the loss actually is different. I will cover it, but the loss is not compared with the correct text, but compared with what the bigger model says.
I'm thinking that when you are talking about student model, it also makes the data set smaller so that you will have more, and you will also save the memory for data set.
Oh, I mean, because the data set does not stay in the memory, it stay in the model, right? The model just learns from it and updates its weights. Yeah, so I mean, the data set is usually even smaller than the model size. It's maybe even smaller than model size. I don't know, like, but yeah, because the model does not memorize the data. It just updates its weights. Here, it updates its weights not. I mean, I said not based on the data, but also based on data. So it's actually we'll see the full loss function. But the idea is that instead of trying to just fill in the gaps, it also tries to imitate the bigger model and its distributions, because the bigger model has already done a lot of effort into learning stuff from the data, and the smaller model is just looking at how the bigger model does and tries to imitate it. And surprisingly, it has been shown to be beneficial. Okay. No, for example, in a certain sentence, I am gap the summer bootcamp. It's like 80% enjoyed, 20% attended. This is the distribution of the output. So in the same sentence, given to the smaller model, the output should be as close as possible to the bigger model. The difference is the loss that we want to minimize in the backpropagation. Yeah. So this was the idea, in a sense. I mean, I'll go over the loss function. Maybe you can have a better idea after that. So yeah, the losses, they have three loss functions that they sum together. One is this. Okay, another example here. India was the first country to grow something, and we want to complete, right? So we have the teacher neural network, which is the big BERT, the normal BERT, not the big BERT, but the normal BERT. Okay, for example, it said mango. India was the first country to grow mango. The student also said the also program here says mango. Imagine in the training point, so the loss is 0. But if it said another word, then they would have a loss and it would have updated its weights. So this is one criteria. It tried to predict that maybe the main label was not mango. That's the trick. Maybe the main label was lemon in the data set. We don't think about the main label at all. Here we just compare with the teacher network. In a sense, yeah. So it's just try to imitate that. As a sense, it would never be better than the big model. We don't expect it to be better than big model because it's just imitating that. And that's also the case in practice. We don't want it actually. So yeah, here you can see. Also, there is another loss, distillation loss, when you compare the whole prediction. So there's the fancy function that compares all of these values together. For example, here you can see another example, the color of a gap is yellow. And the gap is the banana and the most trick, and there are also
Barsa, you're too far from the microphone. We can't
okay,
hear you.
okay. Thank you. So here, I will again. The color of a gap is yellow. So here, the gap is should be filled with banana. Okay. So the teacher provides several examples: apple, banana, kiwi, lemon, mango. But as you see, lemon and mango are also okay, right? They're also yellow. So we want the student model not only to learn it should say banana, but say the whole distribution. So we also say the same thing to the student, and here we see a different distribution. And then the loss is the difference between this distribution and this distribution of scores. The loss is a function of the differences between these two sets of values. And if this distribution was exactly the same at that one, the loss would be 0. And yeah, we define a kind of function. It depends on the implementation to compare these two distributions. So ideally, by backpropagating on this, the student model learns to provide as close plot as possible to the teacher model after a lot of epochs, right? Any questions here? Yeah. No, it doesn't learn on the original data set. We just each time pass one sentence of the original data set to both models, then it learns from the loss computed on the differences between itself and the original model. So initially, it's just random, right? The model is just random. It says something random, and it's improved over time by backpropagation to imitate the larger model over time. Yeah. So this is how they do it. Which is may seem kind of unintuitive, but it actually works well in practice. So yeah. Also they do a similar the loss between the embeddings, because as I told you, also in BERT, the embeddings are also learned in the model. So they also want the embeddings to be high quality. So they also another part of the loss is the differences between embeddings. They sum all these losses together, and that makes the whole loss that the backpropagation is done for. So the loss is composed of several terms when calculating the loss for the smaller student model. A student is the smaller model, right? So here, for example, this is the input, and there are two embeddings. Here is not about the prediction, just about because they also want the student model to have good quality embeddings, not only predictions, but embeddings. So this is the whole process. So we had the loss only for the majority label comparing together in the two models. We had a loss as a function of the whole distribution comparing together. And we have a loss on differences between the embeddings. So these three terms are three different losses. They are summed together. And based on that, the model does the backpropagation. And after a lot of epochs, actually, sorry, maybe we can actually see it's still BERT results. I want to see if we can see the results. Oh, okay, let me show it because it's in the Zoom. Okay. I hope you can see. So as you can see, when in practice they do this, the results are too similar to BERT. You know, they're not far. 92 plus 5, 93 plus 7. So it's maybe just 1% drop in some data sets. In another is also around 1 and 4% drop. In another 2%, 3%. So like it's a small performance hit when compared to BERT. It does not experience a lot of it, but I think the size is like multiple percentages smaller. And the inference time is way faster because the model is smaller and has a lot less parameters. Maybe we can check number of parameters of the still BERT. How many parameters does it have? 40% less parameters than real BERT. And runs 60% faster and preserves 95% of the performance. So it's like at most 5% hits, which is very good. And in many real world environments, we have in our lab, actually, for example, we have made a lot of systems that we wanted a lot of students to use at the same time. So we just use a distilled BERT or a distilled model that has a almost very good accuracy, but it's very real time. It's very fast. As you can see, like 60% faster, and also very smaller. So it can run on devices that do not have a strong GPUs or are not very strong. So it's very good. 44 million fewer parameters. Even people have made it, I think, smaller and smaller, but usually there's a trade-off, right? After a while, if you make the model smaller, then the performance it is more than the benefits. So usually you should find a trade-off in making models smaller. So any questions here? All right. I mean, this is one distillation method. There are a lot of methods that you can distill. They're called usually distillation. Distill the knowledge of bigger models into smaller models. Yeah.
Is it only for NLP or can provide?
I think people have done this for other fields. I'm not an expert in other fields actually, but I think people have done it.
Let's say images.
I think so, based on what I see here. Knowledge distillation and vision transformers. So yeah, it's actually recent, 23. Yeah. Yeah. It seemingly can be done. So yeah. As you can see here, you can see most of them started from NLP, but then it moved to the domain of computer vision as well. So yeah, from what I see here, yeah, people have also done knowledge distillation in other domains. I'm not an expert into them. I don't know anything, but yeah. So this is the original idea. I mean, you can also do distillation in other ways. We will cover one other way, I think, today if you have time. Later, one another way, which is also touches the domain of data augmentation. So we will cover it a bit. But yeah, for now, let's have this. It should be covered after GPT because it's related to GPT. So, okay, let me change the screen again and go back. If you have any questions, yeah. It's Tom, not average, I think. But yeah, in practice, yeah, yeah, it doesn't matter. But yeah, all of the losses contribute to the final loss. Maybe, I don't know, I think there are also some coefficients maybe in the implementation. But yeah, it's a formula based on those three losses that helps in the back propagation. Yeah, exactly like BERT, but less layers, less heads, and this kind of thing. I think they usually remove, like they just make it smaller. The architecture is the same. Yeah, exactly. So yeah. So one downside of BERT was this: we need a lot of memory and inference time. What is another downside of BERT? Yeah, but we fixed them together in one step. So yeah, we provided I mean, there are a lot of more methods as well, but two of the main ones that people sometimes use are quantization and knowledge distillation, which are, I mean, yeah, both of them. Knowledge distillation needs more training, but quantization is usually simpler. You just need to change the precision and map the weights, but it may be not as effective. Another downside was the one that we actually covered from the tool. Anyone remember from the interactive tool that we? No, I mean, yeah, that was not a downside thing, but I mean, the downside I wanted to say is that it can't generate text. It can't complete text, right? If you remember, when we tried to do this, it provided some punctuation and these kind of fancy things that didn't mean anything, right? It can't generate text because, I mean, it's expected that it can generate text because it's trained with a way that it gets like information from words after and before. But in text generation, we only have words until now, and we want to generate the rest. So people aim to, because this was mainly, BERT was mostly, I think, done in Google AI, but people from a different team, which everyone knows, OpenAI, wanted to do something different, which we'll cover now, to have a model that can generate text. Sorry. So about the task of text generation, we have the text in a lot of places. We have for chatbots, of course, ChatGPT is an example of text generation, right? You ask a question and it generates the answer. For translation, it's also a task generation task because you provide the English, and for example, it should generate the translation in French. Also for summarization and a lot of text, a lot of tasks. All of them are quite the same because they predict the next token based on prior tokens. Until now, we said usually predict the next word, but in practice, usually predict the next token. So it predicts the next token based on prior tokens. Maybe if you ask ChatGPT, you see that it types somehow like the typing animation, not just animation, because it's predicting one token at a time, right? Usually these models predict one token at a time. So yeah, this is the whole text generation task. Predict the next token based on all prior tokens. It can be the most probable token. You just predict a model to predict the most probable token at each step. The token with the most probability that can come. So it's a kind of multi-class classification. Because if you, why is the kind of multi-class classification? Imagine you have a classification model that classifies a text onto the whole vocabulary size. It's a kind of classification, right? And the number of classes is the vocabulary. So you just predict the next word, which is a kind of multi-class classification, but the number of classes are maybe a billion, like all the words in the vocabulary. But the spirit is the same. So it's the multi-class classification. It returns a score per word, and you just use a softmax to convert them to probabilities. So you have one probability per word, and you can pick the maximum probability at each time to find here. For example, I asked ChatGPT, why NLP is so exciting? Then the next probable word that would come is the word natural. Here, the model, after we input this to the model, it provides a softmax score for any word in the vocabulary. For example, the vocabulary of the word eat, the probability of the word eat, maybe 0.3. The probability of the word something else would be something else, but the most probability is the word natural. So it outputs it. Then it again inputs why NLP is so exciting, natural to the model, and then the most probable token is language. Then the same thing all of the year, the most probable is processing, and it goes forward. So you can output the next probable token, and actually it's very interesting that it works well. Like just outputting the most probable token sometimes helps. There are some changes to it. Otherwise, the lecture would have finished by now because there are some changes to it and it's fancy stuff that people have done that we'll cover. But the general idea is that one at a time, then use for next token. Also, sometimes we call it autoregressive. It's a fancy word which means the same thing. Like you provide one token at a time, then you add the token back, and then you predict the next token. One interesting thing here is that, yeah, we just covered it, so nothing interesting. So yeah, now you know how this one token at a time works. So if you have a model that has been trained to predict the next token, it will be useful for text generation. And that's what we can use transformers for. If you remember for BERT, we remove this part, the right part. We only kept the encoder. Now we want to do the exact opposite. We remove the encoder and we just keep the decoder, right? Here we want to exactly do the like the vice versa stuff. Like maybe also with picking the encoder would work, but the way that it was done and made successful was that they removed the encoder and just pick the decoder. So here, as you can see, this is just the decoder. I mean, it's another diagram, but it's the same thing, right? We have the embeddings, we have the mass attention, the layer norm fit word layer norm, and just the decoder. There's one difference here. So in the decoder, we had two attentions. One was on itself and one as the encoder. Because we don't have the encoder here, we only have one attention. So the transformer decoder removed this attention that was on the encoders, the second attention, and we only keep the first one. That's it. This is the basic model. We repeat 12 items, blocks of this. And this is called generative pre-trained transformers or GPT, right? So this is the GPT architecture. We just pick the decoder of the transformer, we do some modification to remove that part that depended on the encoder, and we repeat it for 12 times. 12 was the one in the first, I think, GPT paper. So any question until now? How the architecture of GPT is right? Fine. Yeah.
Maybe you'll answer this afterwards, but is it that these structures are trained as a transformer and then the decoder is the part that's used?
Oh, I think no, we train from the beginning without the encoder. Also, the BERT was the same. We trained from the beginning without the decoder. So yeah, and actually today we are talking about two specific versions of transformers that have been useful for NLP, right? You can also use a full transformer for NLP. You can just treat it as a time series and work. But these two architectures are so famous, BERT and GPT, and each of them keep one part of the transformer. That's what we are covering today because they are the things that you use the most when dealing with transformers, when dealing with NLP task. But yeah, I mean, you can do a lot of differences on your own. You can add something to this architecture, remove something, and call it your architecture. But if it works better than everyone in the research community would use, it's usually the case like this. So it depends on if it would work well or not. But as we saw here, yeah, they first remove the architecture and then start training. So yeah, they don't include the encoder at all in training GPT. Yeah. Any comment? Question? Let's go. But this thing is over my slides. Let me remove that. Here. Okay. So how did they do the pre-training of GPT? Again, okay, GPT is also these two-way method. Like you can also pre-train and fine-tune it. So the same thing for BERT again applies here. The same transfer learning. Actually, the main difference is that GPT is first from based on decoder, not encoder of transformer. And the second is that it is a generating model that we will cover. So it's pre-trained on a lot of text. Actually, I think the GPT-1 was pre-trained on 7,000 books, 7,000 full books, which is 13 gigabytes of data, like full text of the books. It was the training data set for GPT-1. GPT-1 was, I think, announced 2018, 2019, or somewhere like that. But how did they do that? They picked chunks of 512 words at a time, because you need to have a certain context length. You can't put the whole book into the model and say, please learn from it. You have to provide into chunks so that it fits into the context of the model. So they split it into chunks of 512 tokens at a time. And then what was the criteria to predict the next word at each chunk? So you just mask the word. For example, let's start from the beginning. The next word will be am. So it would predict the word am. I am, then the next word, and so on. The job of the model was to predict the next word. And that's the criteria. The last was defined on that. At inference, the input is a partial text, very obvious partial text, and the model generates tokens one by one. Right? So this is very simple, right? It generates tokens one by one. What's one difference we have here in training and inference, which is actually kind of important? Imagine this sentence: I'm attending the summer bootcamp. In training, you provide it like this. After I, it should come am. After I am, it should be attending, and it would compute like this. Imagine at the step I am, maybe the model says something else, like I'm enjoying, right? Okay, you correct it via backprop, but in the next step, when you want to say predict the next word, you again use the ground truth, the truth from the data set. You don't use enjoying that the model said. You know what I mean? Maybe I can write here. People won't see. Maybe I can just say, I should have put it in the slide, but yeah. I am enjoying the summer bootcamp. After I am, the model may in the training, maybe it predict attending. Something else, right? But in the next step, when we want to predict, when we want to train the next word, we again use the data from the book, not from what the model wrongly said. It's fine, right? I think you assume also to be the case, right? If you want to train, we want to train with correct data. We don't want to include the error of the model into the prediction. But there is one challenge. When you use GPT to generate text in real world, one token at a time, if a model makes an error, it would continue making that error, because it will be added back to the data to like generate the rest. For example, if in the practice, instead of I am attending or I am enjoying, it said something very bad, for example, I am eating, then it can't complete the sentence in a good way, in any ways. So this is a difference between how they are trained and how they are used. And that makes working with GPT a bit tricky. In metric, in training, you can see very low losses, but in practice, they may not work well, or they may say wrong things, which actually happened a lot. I mean, now GPT is strong, but GPT-1, GPT-2 is very trash. I will show you some examples. So that's the thing. This is a very specific challenge to the training generative models. So again, I'm saying, in training, at each step, you use the real sentence from the book to predict the next word. Just you predict one word. And then for the next word, you again use the full sentence from the book. But in practice, when people are using it, except the first word, maybe except the first word, every other word is predicted by the model. So the model, actually the data that the model is working with is different from the data that it was trained on. The data that the model was trained on was from the book. But the data that the model is working with is a mixture of user and its own wrong sentences, its own maybe not so correct sentences. And thus it makes the model sometimes not work well. So this is always something you should always remember when working with generative models. Sorry? I don't think there's any certain thing. So that's the challenge. I mean, people have been improving GPT a lot, and now you may not think it has this problem, but that's not because I think they have fixed this problem specifically. It's just that the model has got very better so that it can find this. I don't think people have fix any specific problem for this, but this is always a challenge that you need to have in mind, so that if the training loss may be very small, but in practice, when people are using it, it's not helpful. So it's a difference between you know, if you evaluate it, even not training loss, but the test loss on the book. If you just provide test loss on the book, it may be loss. It may be very low, and accuracy would be high. But in practice, when people are using it, it says your system's crap, and that's the reason. So you should always think that there is a disparity between what the metrics say and what people in the real world observe. All right. And by the way, GPT can be fine-tuned also on a certain data set and domain. For example, GPT-1 was trained on 7,000 books, but imagine we want a model that helps writers write, for example, drama books, like books about drama and like drama stories. We specifically can fine-tune this model on 100 drama books that we have, because maybe we can't find 7,000 books because you need to buy all of them and there are permission issues. But imagine we have 100 drama books. We can fine-tune the model only on drama books and expect it to output results similar to drama stories. Or we can fine-tune it maybe on a code documentation and expect it to be able to answer questions about code. For example, we can fine-tune a GPT model maybe on the Stack Overflow, and we expect it to be able to provide solutions to code problems, something like that. So we can fine-tune the models. I mean, this is, you don't fine-tune GPT-1 anymore. GPT-1 is now super small compared to the model that we have. 13 gigabytes of data is nothing for a good generation model. And we can see some examples. We'll cover it. So yeah, this was about the fine-tuning. So again, there are two steps. The pre-train is on a lot of text, again, in a self-supervised manner, and you can also fine-tune it on a certain data set. Any question? It's fine. Yes, there is one way to address this specific thing. In a sense, to an extent, you can address this. We will cover it. But in general, if you go for some tokens wrong, all sentences will be crap in GPT, because each token depends on the previous tokens. And you should really pay attention that all your tokens are good quality. You can't easily go back in time. So GPT does not have the ability. Maybe you have tried ChatGPT, it never deletes text that it has written, because they are not built to do this, right? This model only outputs the next token at a time. So anything it starts with, it gets stuck. Sometimes we can see that GPT starts in a loop. Maybe if you have tried some prompts in ChatGPT, it starts with telling you something over and over that you say, no, I don't want this, but it's like that. That's because of this reason. Yeah, it unfortunately happens. This is the downside of it. Yeah.
So you're saying that the output can be wrong. What is it? What's the metric of being actually wrong?
That's a good question. I didn't put it in the slide, but I can talk about it later. So there are some metrics for evaluating text generation models. You can compare them to the reference things from the book using the number of words that are shared or the number of expressions that are shared. Or something else that people are doing it now is to use benchmarks. I don't know if you have seen like benchmarks for GPT and versus Google LLMs. So benchmarks are a specific set of question and answers. For example, imagine like a question is that I should say, like there's a yes/no question that you expect ChatGPT to answer well. And if the model answers well, you give it 1 point, other you give it not. And then you compare different models. There are some benchmarks that you can compare LLMs
So
with.
they're curated data. It's not even a data set, right? It's a curated.
Exactly. And they don't train on that. So it's a kind of test data. Yeah, exactly. Yeah, exactly. So, but actually there's a trick that sometimes data gets introduced to the training data set indirectly. I will cover it. So you can't always, one problem with generative models is that, specifically now, you can't make sure all training data is separate from testing data. I will cover it. That's a trick actually, but I'll cover it later. So any question until now? All right, let's go. So then they moved to GPT-2. This one is trained on web data, not only book data. They increased the size to 40 gigabytes, so more data. They provided 4 sizes. Here you can see one example of how it's works, and it's crap. I liked attending the summer boot camp. The completion is blue, but I didn't want to go to the summer camp. I wanted to go to the summer camp because I want to learn how to do it. I want to learn how to do it. This is crap completion, right? But if you see the training, actually the training was good. Like the loss was low on the book or the web. But because it's said, yeah, if it said, but I didn't, for example, it goes to a very bad direction and it doesn't know how to answer well. So in practice, sorry, it's not okay. If you think it's nice, then it's nice. But yeah, so in practice, yeah, GPT-2 was not useful for, and nobody could build a like good chatbot with it. If you, I mean, maybe you think that, but if you go to a company and build a chatbot, you think the customers would come to you and say, "What the hell is this?" But yeah. But you can see that at least it knows the grammatical structure, and that's actually a positive point. Like it knows how to follow the grammar. The grammar of sentence is correct, and it doesn't know anything about how to form an English sentence. It just learned this from this training data, which is actually impressive. Like it learns the grammatical structure automatically. We don't explicitly tell the model about grammar. It automatically learns them from the data, which is very good. That's why we need to make sure the data is in good quality. If the data is crap, wrong grammar, the model will also learn it. And that's very bad. So we need to always ensure that our training data is very good quality. Just saying. So any questions on that? Move to GPT-3, 175 billion parameters. So they jump in the quality, and you can see that it works better. I think summer bootcamp, it turned out to be more than just an addition to my knowledge, but also level up my C# skill. I don't know why C#, but at least like it's way more meaningful than GPT-2. You can easily understand the difference. But there are also some random stuff here. I don't know what that is. So yeah, the model at least works a bit better, which is good. We can suggest that by increasing the number of parameters, the models are able to learn better and better. And GPT-4. I liked attending summer bootcamp because it offered me an amazing opportunity to learn new skills and broaden my horizon. You see, this is like very professional written text. Imagine like an English expert had written this. You can see how the changing of the scale of the model really improves the generation quality. Two things have changed, both the size of the model and also size of the training data. We don't know the size of training data for GPT-4. OpenAI doesn't tell us that. I don't know, like corporate secrets. Yeah, and also the size of model, we don't know. But of course, it should be more than GPT-3, like obviously. And we can see that the more size is really helpful. This text is like a quality, and that's why everyone now is scared that people are doing their assignment with ChatGPT, because the quality of this text is much higher than we can confuse them with a real human.
They're also trained on the conversations, right? Like
Exactly. Yeah, I talked about conversation specifically. Yeah. So this is actually a bit of because GPT-4 is not only just GPT-3 made bigger, or GPT-3 was not also only GPT-2 made bigger, but yeah, I'm just simplifying. I'll cover some of those lists. So yeah, about the decoding, we said that okay, GPT decodes one token at a time. It finds the probability of each token in the vocabulary to come next. We can do it by softmax, right? We have a set of scores, and we can put in a softmax function to find the probability for each token. For example, the GPT wants to complete the weather in summer is hot is this probability, warm is this probability, and cold is a small probability. One question, should we always pick the most probable word? So this is called the greedy, we call it greedy argmax. We always pick the most probable word at each step. For example, we always hear pick hot. This works good because it means that it's a better word, but the problem is that it's deterministic. It's always the same response. For example, ChatGPT is now like this. If you ask the same question from ChatGPT 2 different times, you get different wordings, right? You might try. Like if you ask the same question from ChatGPT 2 different times, you have different wordings. And the reason is that they don't just pick the most probable word, but they choose from some top ones proportional to their probability. For example, with 60% probability chooses hot, with 30% it chooses warm, something like that. The probability can depend on the results from the softmax. However, you may think it may choose cold, which is wrong here. And that's right, you can cap it. to an extent. For example, you can say only consider the ones probability above 0.25. And among those, you can pick one of them randomly proportional to their probability. For example, here you can put the cutoff here, and then you can say, yeah, with 2/3 pick this, and with 1/3 probability pick this. This is the approach that they usually do. Another downside, if we don't pick the most, if we don't do this, is that methods love to write repetitive text. You can try this. Even in our example, it's love to do that. I wanted to learn how to do it. I wanted to learn how to do it. You see, it's a repetition. Because the word has already come in the text and thus has a higher probability to come again. And this leads to repetition. This mitigates repetition, in a sense. If you have some probability of choosing not the exact next probable word. Actually, there have been some simulations on humans that have shown we don't pick the most probable word usually when we are speaking. And they actually compared it with GPT and said, yeah, actually maybe GPT should be more closer to human because we don't usually pick the most probable word. We don't think logically about everything that we say, right? We just our brains doesn't just find the probabilities per each word and find the most probable. Our brain doesn't work like this. And this is somehow to make it closer to humans, to have some randomness, some stochastic process, some randomness in the process of finding the next probable. So any questions? All right. So we don't only pick the most probable word usually, but I mean, you can also pick the most probable if you want to result for it to be deterministic, but that's another case. Yeah. Another idea that they use for reducing the chance for models to make mistake is a beam search. What's that? At each step that you want to predict the next word, instead of one word, you predict a number of words. For example, B word. B is the count, right? Imagine B is 3. Here, I think B is 2. So you predict 2 words, 2 next probable words. It can be the top of the list and the one to the top, for example. You pick 2 probable words, and then you continue each of the branches. At each time, you keep the branches that have the higher probability. For example, you can at each time have for example, 3 branches that have the most probability. And finally, in the end, pick the most probable branch. How does it work? For example, here, arrive there. It's a start of a sentence. They arrive. We predict the most. Like, imagine in the start, these are the 2 most probable words. We just pick them. Okay. Then to the next word. After arrive, they and which. Then after they, green and which. Okay. These are the words that we are predicting. Then we compare these probabilities. We see that among these 4, the 2 top ones are this and this. So we discard this. For example, here the K is 2, the number of ones to keep. Then again, the next step, the green to like this, and which also to these 2 words. Then we again discard these 2 that are the least probability and pick these 2. So now we have 2 branches, the green which, the which arrived. You see? And then again, we continue. For example, here we predict the end and the which arrived. So the green which arrived and the which arrived. These are the 2 sentences. Which one has a higher probability? We pick that one at the end. So what's the reason? Anyone understood how do we do this? So it's the same thing, but we do multiple branches at a time, and we pick the ones that have more probability. One reason to do is I actually have an example from the NLP course here, which was a very nice example because it was in French. It was like sometimes, for example, in French or in other languages, you may use certain verbs that they don't translate literally to their English ones. For example, I think in French you use the word on sometimes for V, but sometimes for general facts. For example, on full something. Maybe French people know here better. On full, can you give an example with that? Yeah. What's manger? What's that in English meaning? We want to eat. Okay, but I think on had also another meaning, right? If it was for factual information. Yeah. I think that was the word on that had 2 different meanings. One, it can like not mean V, but it can mean something else. I don't remember, but sorry.
Yeah, exactly.
Because yeah, I don't know it either, but actually,
It's not about a 6. It's
oh, I see, I see. Okay, yeah, I mean the example was like that. What I want to say is that sometimes if you start translating literally, you get into a trap. Because yeah, you know, and here we avoid the trap, so we have multiple branches, and maybe after a while one branch hits a dead end, and we saw this branch was not successful, so another branch would help us. So this is the general idea behind beam search. That would help us if we go multiple branches at a time. Maybe one branch in the beginning is less probable, but in the end we find that that branch was more probable. So this is the idea behind beam search. It usually, I think, done with more than two. Two was like very toy, but just wanted to show an example here. Just found this from, I don't know where, I put the link here, from Stanford. So yeah, that was the example of two branches, but in practice it can be more or less. And
Can I give a comment?
yeah.
I didn't say this in audio lecture, but in automatic speech recognition, so speech to text, you can also use beam search to improve the quality of the predicted text. And the idea is exactly the same.
I see. Yeah, I assume that because in the beginning of the audio, you may hear a word differently, but in the end, as the text goes forward, you see that, oh, the other form of the word made more sense. Yeah, like
It's
that.
basically for each time step we have like some of the tokens, but the final predicted sentence, like for text, can have another meaning after several starting points,
Exactly.
as you said.
Exactly. Yeah, exactly. So as I said, we can also apply to other domains. This is usually called beam search. You go to different beams like directions. And also you can either use top K, pick the top K branches, or top P. What's the difference? Top P usually means any probability more than a threshold. So for example, if you have 10 branches and your threshold is 0.25, you pick all branches with a probability more than 0.25. It can be only one or all of them. You just put the threshold on probability, but you can put the threshold on the count of branches that you keep. So both of them are, you can do it. You can either pick, for example, top 5 ones or all the ones above a certain probability, or even both, like all the ones above a certain probability, but a maximum of 5 of them. So you can play with it, like pick some of the branches. This is the strategy that you pick to pick the branches. And I think we don't know that how actually GPT-4 does it because nothing is out. But for earlier GPTs, you can see, yeah. I mean, yeah, but you know, all the branches grow. So the length of the sentence is kept quite the same because, you know, all the branches grow together, right? So the length is not a factor in comparing branches. It canceled out. Oh, okay, yeah. So that's a nice thing. There are different strategies if you reach end, what you do. So usually end is the token that you also predict when the sentence finishes. And there are different strategies here. I also wrote a sentence here. So it really depends on the implementation. You can, if you reach end, you can continue to a certain limit and then stop. You can directly stop. You can do a lot of things. This up to your implementation, exactly as what you do. Yeah, this is different between implementations, and you can choose one strategy that you think works. But I mean, in practice, because you know this doesn't depend on the training of the model. It's just for inference, right? So you can train the model and then play with it until you find the best inference strategy. It's very easy. You don't need to train the model again. You have the model. This is just for inference. So you just you can, I mean, you can just have this for inference and play with different top K, top P, or the ending strategy to find the best way. Any questions? Clear everything until now? We have some time still. That's good. Another thing that I want to introduce here, maybe you hear a lot if you work with GPT, is the temperature. So we had the softmax, right? You remember? The softmax was a set of values that you compared to exponential and divided them by the sum of all exponentials. A way to convert scores to probabilities, right? You remember all softmax. We have another thing called temperature, which you divide the score by a temperature before giving it to the softmax. It's a scaling factor. So temperature is the tau here. It's e to the z of I over tau. Temperature is a way to control how softmax behaves. If the temperature is 0, what happens? I mean, the temperature could not be exactly 0 and because it's exponential, but imagine like it goes to 0. I mean, you can set it to 0 and it would have an edge case that code can handle it. But if it goes to 0, this number would be I mean, yeah, but I think 0 is an edge case that is defined actually separately.
What's at the same probability?
I mean, yeah, I think actually if you increase the tau, it will like this. Like if you increase this division would be closer to 0. So this would be closer to 1. And then it would be 1 over a sum of 1s. If the temperature, for example, is 1,000,000. Imagine your temperature is 1,000,000. Sorry? Yeah, exactly. It will be uniform because the practice happens like this. If you increase the temperature a lot, this proportion goes to 0. So this thing goes to 1. The whole exponential goes to 1. It will be 1 over the sum of 1s, which is exactly the uniform distribution. So in large temperature, it will be more uniform, so a higher diversity of the words that would come. In a very large temperature, in fact, the model does not do anything. It will be just random word selling, just saying random words, right? So you should not increase the temperature beyond a certain amount because it will be close to random, right? But the temperature, as you decrease it, it will be closer to only outputting the highest probability. In practice, if you set it to 0 in code, and 0 does not work in the formula, but if you practice 0, it would only return the highest probability. So it would be equivalent to the greedy one, that we just pick the highest probability. We don't pick the rest. So this is the temperature that you usually play with it. For example, maybe you have seen these kind of online tools that you want to chat, and there is a creative version, and there is a more strict version. I don't know, like in Bing search, if you have seen, you can fix it to be more creative in answering or be more strict in answering. They usually play with temperature. If you increase the temperature, it's higher diversity, and to humans, it's like, oh, the model is more creative and says more fancy stuff and more unrelated stuff, jumps from a story to another. But above a certain temperature, the output is garbage. So you should also pay attention to this. Actually, we maybe, and I have to say also the temperature values that usually work are mostly between 0 and 1.5. So it's not, we are not dealing with temperature like 100,000. It's like that. Usually the scales are between 0 and 1.5. I think above 1.7, GPT starts to give garbage answers or something like that. Even GPT-4.
I'm not sure, like, can we adjust it?
Yeah, not on ChatGPT, but I will show you on the, if you create an account, I mean, with the same GPT account, you can go to platform.openai.com. It's the developer console, and you can then adjust. Yeah, I'll show it actually. Yeah, it's a part of plan if you have time. So yeah, exactly. So we can adjust the temperature and change the diversity, which is very exciting. Okay, we saw how GPT is trained, but the interesting thing is some behaviors about generative models emerge at a scale. What does that mean? Emerge means some behavior happens to be that was not there before. But at a scale, we mean when we increase the size of the model a lot. So BERT was 400 million parameters. The normal GPT-1 was around the same. Like GPT-2 was maybe 1 billion or so. But GPT-3 jumped to 175 billion parameters. And GPT-4, I don't know how many, like maybe a lot, right? So the scale increased a lot. And we had some interesting behavior from generative models that we didn't train them for, but they happen to be. And we want to see some of them, which are pretty exciting. So before that, you remember that we said we can also train transformers with both encoder and decoder, right? You remember that we can say also there are some models that include, we said BERT removes the decoder, GPT removes the encoder, but we can also train some model with both of them. Actually, there was a successful model called T5 that does similar like this. And the model is trained on a lot of instructions, like translate. It can do translation and summarization and a lot of tasks. So it somehow learns this. I just wanted to say, yeah, these are also encoder to decoder models. It's not the topic of today, but anyways. These models are getting bigger and bigger. This is what I said. This is the original transformer, 65 million parameters, BERT, 300, it says 400, but yeah, 300. GPT-2, 1.5. then the T5 that we just saw, GPT-3 here, and like, okay, this is until 2022. Just in past 2 years, we had GPT-4 and like a lot of great new models. So I think now if we plot until 2024, maybe that one is here, and then we have a lot of more bigger models here that we even don't know how much big they are. 15,000 increase in 5 years, and now it's even more. So because of the GPUs, like NVIDIA is like selling GPUs like hotcakes, and everyone is purchasing GPUs to train their big models. One interesting behavior is this. It can follow instructions, not only generate text, but answer questions. For example, this is GPT-2. Write the capital city of each country. Germany, Berlin. France, Paris. Italy, it said Rome, automatically. So it somehow found a pattern in the data, and thus we can use this model to answer questions. This was the first time that researchers found that, oh, we can use generative models for chatbots that answer questions. Because until then, it was more like complete this story for me and things like this. Like here, they saw that with this approach that provides some examples, some pairs, it can expect the model to return a new entry for us. Spain, Madrid, Sweden, Stockholm. But for example, see Switzerland said Zurich. Is Zurich the capital of Switzerland? Why do you think that happened? Sorry? Maybe it is. We trust GPT more. Like, for example, GPT-4 doesn't have this problem. If you add GPT-4, it says Bern.
It's interesting, like, so it's this model is just reflecting people's wrong assumptions because most of people also in Switzerland think they live
And I think because maybe the name of Zurich happens more with the name of Switzerland, so the co-occurrence is higher. Because it is never trained to find capitals. It just infers them from data, you know? GPT-2 was not trained on Wikipedia. It doesn't know the capitals. It just has seen, for example, books, I think, that use the names together. For example, if a book talks about Italy, the stories happen in Rome. If the books talk about, for example, if the book talks about Germany, the story happens in Berlin, like France, Paris. So Italy should be Rome, and like this. It infers automatically, and that's very interesting that this behavior emerges at a scale. But as you see, this behavior has traits, has wrong and stuff, but if we increase the scale of the model, it improved. Never OpenAI, I think, told GPT-4 the capital of Switzerland is Bern, you should not say Zurich. It automatically learned it when the scale went bigger. So it's just a matter of learning more. We usually call it in context or few shot learning. Here, we have not trained any model to find the capital of a country. We just rely on a model, even not trained on country data, maybe trained on books. But it can help us find the capital of each country. And very exciting, like GPT-2, an old model, I think maybe for 90% of the countries in the world, it works correct. And also for Switzerland, I mean, it's working correct from its opinion, right? It's somehow providing the most important city maybe in each country, if you consider it like that. Which is maybe Zurich for Switzerland, from like economical stuff. Yeah. Maybe if you for US we try, maybe it would say maybe New York instead of Washington. Maybe. For the same reason. But yeah, so this is the thing. We usually call it few-shot learning. It's different from traditional learning in which we don't update the gradients. We don't do backpropagation. We just include the examples in a prompt. We call it a prompt usually, what we input to the generative model. We input the examples in the prompt, and then we have a gap so that it fills it. And this way it can answer questions. So they found that, well, we can use it for chatbots to answer questions of people. Another thing is zero shot. In zero shot, we even don't put examples. We just ask the question directly. The capital of Italy is, and we ask the next token, and it's wrong, which is correct. I mean, the generation is crap here, and the capital of the world is wrong. Wow. The city of the Rome is the wow. Okay. Of course, the generation is crap, but if you just check the first token, it answered our question correctly. This is called zero shot, which means we only ask the question. We don't provide some examples. Usually few shot works better. Even, I mean, for a simple task like this, yeah, you can use zero shot. But if you have a very specific task, like in your work or anything, sometimes zero shot doesn't work well. And you need to provide some examples for the model to learn from. Here, again, I'm saying learn is not gradient updating or backpropagation. By learn here, I mean just inputting in the prompt. And it's very exciting that just from the prompt information, the model can work and provide us with the answer. Certainly, the quality can differ in more difficult questions. For capital, the zero shot was successful. But here, From GPT-2, I ask, what is the code to print hello world in Java? And see the answer, the code to print hello world Java is Java, the language. What's this? It was not able to provide me the output code, you see? GPT-2 was not able to do. So for zero shot, it was not able. But better models are better. Here, what is the code to print hello world in Java? You can see the code is correct, actually. So, and also writes the output for us. This is GPT-3.
So here you're showing us question and answer, almost question and answer text generation.
Yeah.
You're calling that zero shot learning.
Yeah, they usually called in literature zero shot learning to say it's different from few shot learning, but it's not a learning. It's just called in the literature. It's not learning at all because it's not learning anything.
But this is also just prompting.
Yeah, just prompting. In official literature, it was used to, and still some people call it zero shot learning, but it's not learning at all. We usually don't use learning word a lot these days. We just call it, we prompted the model zero shot. We usually write in papers like this. We passed a zero shot prompt, by which we mean we didn't pass any examples. When we write, if you in a paper, you see, we passed a zero shot prompt to the model, which means that there's no example. They just ask the question. If they say we passed a few shot prompt, it means that they included some examples, which can be useful in some, usually you need to provide some examples for the model to work well beyond simple questions. So there's something about it. Okay, you can see here the hello world was successful in GPT-3. But even in more difficult tasks, it can be even worse. Like here you see, write me the code to train an NLP emotion classification LSTM-based model using PyTorch. Answer, I'm not sure what to call it. I'm not sure what to call it. GPT-2 is crap, but GPT-3 gives me the code. Which is pretty exciting because GPT-3 was not specifically trained on code, but it provides a working code. And that's very interesting because in the vast training data, it has also seen code and has learned it. And this is something that still many people in the world don't know how LLMs, how large language models and generative models can do this. Like this is a miracle, but it happens to be. Like these models can output a very good code, and I think that would run.
Even the earlier models of GPT, the syntax of the code at least.
Yeah, so here, actually GPT-2, as you see, the grammatical of the sentences are correct. But the data was not enough to learn something like that. When the model, both the number of parameters and the amount of data increased, the model was able to learn a lot more and was able to help a lot more, as we can see here, which is pretty interesting. So the whole field of prompt engineering came to be. Prompt engineering is to find the best question you can ask from the model to give the answer that it wants. And people are actually going crazy on it. Like you can see a lot of Twitter accounts, best way to ask a prompt from ChatGPT, how we can ask it to provide something and things like this. So this is the whole domain, because these models also depend a lot on the prompt, specifically in the zero shot manner. There is another emergent behavior. Another behavior that's very exciting. Imagine we ask a question that needs reasoning. For example, the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? If we ask I think this is GPT-3, if you ask it to provide the answer, it would say the answer is 27, which is wrong. But the model does not have any thinking behavior, right? How should it find the correct answer? It's just predicting the next word, right? How the model should predict the correct number here from what we learned. Do you have any idea? Like the model can't, right? The model is trained to predict the next most probable word. The model is not trained to calculate numbers. And thus here the number is just 27, maybe just was picked from the top K randomly. So it's not correct. But people have found some way to ask this kind of questions from GPT. Ask it to think, which is very exciting. If the model starts to think, it will give us the right answer. Because the cafeteria had 23 apples. This is okay, just copying from the input, so it's fine. They used 20 to make lunch, so they had 23 minus 20. And here it can't find 3 because in a lot of training data, this was here. The 23 minus 20 was here, and it's a simple calculation that it can memorize, can have memorized from the training data in a sense. So if in the training data somewhere in some documents 23 minus 20 was there, it knows that 23 minus 20 is 3. So it can just output 3 as the next probable letter. It's not calculating. It's very interesting that it happened actually. It was a very seminal paper and it changed a lot. and then they bought 6 more apples, so they had 3 plus 6 equals 9. It usually knows these small numbers, and the answer is 9. And now the answer is correct. The model has not done any addition or any kind of addition or multiplication at all. It just outputted the next probable word, but the answer is now correct.
So I just wonder, like, it's just interesting that they don't know the calculation parts, and they just making it just based on pure statistics.
Yeah, it's very interesting, and like from when I saw it for the first time, it was like, wow, it couldn't happen. And it's actually recent, like 2022 people found this. It's not something that has been known for a long time, but after that, this was before the ChatGPT era, months before that. And after that, it was like everyone knew it, and like the new AI era began, that everyone is now using AI. And usually in your examples, if you want ChatGPT to give good answers, you can ask it, let's think step by step. If you usually add this in the end of your prompt, it would think like this and would give you better answers. There is another trick that GPT is now using. If it recognizes numbers, it calls a calculator module and gives the numbers in the text to the calculator and returns the results. And then the model also uses that result in a way to predict the next token. So this is also another trick. This is an external calculator module that at each time calculates the different, for example, here, when they reach 23 minus 20, here, instead of outputting 3, the calculator identifies the mathematical expression and calculates it and output 3. So this is also another trick that now I think you can use it in GPT, ChatGPT.
Also access to the calculator if it is just like purely.
Oh, but ChatGPT is not. ChatGPT is a system, right? So when it's predicting the tokens, at that time, the system, like the code, doesn't ask the generative model, otherwise ask the calculator, for example. Yeah, I think you can play with it, like to have access. You may have seen that ChatGPT can have access to the web. I don't know if you have seen it. It can search the web for you. It's something similar. So in some place, the generative model stops. It goes to the search and prints the search results, and then the generative model starts to generate the rest of it. So yeah.
So I mean, like, if we model on the text, let's say all the addition, like give the examples of the additions, and then after it should be able to learn the pattern of addition.
But do you have all the addition in the world?
Not
in the
all the
data?
addition, like most of the additions, but it should be able to make out and then generalize to it, right?
Yeah, actually, this is what he's doing now. So ideally, in the training data, there has been 23 minus 20. And thus it knows the answer is 3.
But the question is, what was the order? Can we know the order and say that the order, and from the statistics, they might not know the order.
Oh, okay, that's a good question. I think it doesn't have any idea of the order of the numbers, but the embeddings can have some meaning. Maybe the embeddings can are in a sense that it can know some semantic information of the numbers. But usually these are black box things that we don't understand if we just look at the embeddings. But the model somehow understands. Did you see the recent actually example? Just 2 days ago, I saw in Twitter, they asked some generative models, which number is bigger, 9.9 or 9.11? And some of they say 9.11 is bigger. Maybe you have seen this in Twitter or like in social media. Because it somehow thinks that 9 is another token and 11 is another token. So 11 is bigger than 9, so maybe it's get confused. So
It takes like the number as a strings, right? And then
yeah. But even if you think as a string, 9.9 is bigger because 9 is more uniquely.
Maybe they're just, canceling out the side.
Yeah, I mean, the thing is, we think about this, but LLMs, like models, don't do any of this. They just predict the next probable token. And that's the interesting thing. And we just want to guess what predicting the next probable token would be happening. Yeah, with the calculator module, these things would be solved. And I think people have actually used some of them calculating stuff, but yeah. So this is the thing. Any question until now? It's interesting, right? Any question?
I think people will get stupid.
Yeah. Still, another catch is that this is not enough for a useful chatbot because we need to align with the human expectation of a nice output. Here. Yeah. What are the differences between a Mac and a Windows PC? I just asked it. The answer GPT-2 is, of course, the Mac is a very good computer. It's a very good computer. It's a very good computer. It's a there. Okay. Here, GPT-3 is more coherent, but still, in the past, Macs were considered to be more user-friendly and easier to use. However, the recent advances is no longer the case. I think Apple, if sees this sentence, they would sue OpenAI, right? So this is usually not the way that you write to a human that will like it. There is some tuning to align these models. The way that we do this, we only cover it very briefly because it's a domain of its own. It's called RLHF. It's reinforcement learning from human feedback. Okay, reinforcement learning is a topic on its own. I won't enter. But the idea is that we start with a base language model. We train a reward model that returns a representation of the preference of humans between two outputs. So the way that we do this is that we show different outputs from models to humans. We ask them to rank which one they like better. And we train a model on the differences, on which one the humans prefer. And then we integrate this in the training process of our language models. The way that we do this is with reinforcement learning, which is a topic on its own. I mean, it's not also my expertise. I will not cover it. But the original idea is that they provide some preference data between outputs, ask humans which one do you like better, and then they use the outputs, they use those outputs in the process of training the model to make them align better with what humans expect. For example, here, if we show this example, maybe I think I have the example here. So this is the example that we saw, and this is the example from GPT-4. Actually, not GPT-4, this GPT-3, but with RLHF. With this approach, this is the exact GPT-3 model, but with this tuned. You can see the output is way better. Here, compare this. Here it started in the past, Macs were not considered something like that, but here there are several differences, including 1, 2. You see, it's like very well structured. It's the same model. It's not GPT-4. It's the same model, but tuned with this approach. That makes the output way more coherent and better aligned with what humans expect of a nicely written text. So the way OpenAI did this is, I think they hired a lot of people just comparing different outputs. And yeah, sorry. They hired a lot of people just comparing different outputs and picking which one do they like better, and then they used them into training their model. As you can see here, this is a way of integrating human feedback for improving our models. LM is language model, such that it follows the instructions better. And that's why you may see GPT loves to please us, loves to make us happy. For example, if you sometimes you say something, and it says no, it's wrong, and then you you ask something, and GPT tells you something, and then while it is right, you just tell GPT no, you said it wrong, and then GPT says, I apologize for that, you were right, but it loves to please you because it's trained to do that. It's actually trained to provide responses that humans like more from this process, which is very interesting. You can see an example here. I'm sure everyone who show these two responses would say this one is more structured, and that's the case. So they provide a lot of inputs. I don't know how many. I don't think OpenAI has announced how many entries they have done, but yeah. But there are some downsides. This is actually, I don't know if you have heard or not. This was okay. Before that.
So you said the model, the foundation model. Did you know what's?
I think it's a part of fine tuning, but I'm not an expert on that. So it's including another model, which is the RL model, in the process. But actually, I don't know much about that, to be honest. Like I don't know about the technical implementations a lot.
Do you know if it's been published or they keep?
Yeah, this one, the main architecture was published, and actually some open source papers have done this. The one that is not published is that what is the data set that they have used, or how many examples. Yeah, the original model is known. We have the code for that, yeah. But I mean, I don't know much about the code. It's outside my expertise at all. But yeah, the data and the specific, like how many examples human rated and how they rated, like details, no, these are not published. There are some downsides actually to this way that LLMs are trained. Maybe you have heard this about the word del. How many of you have heard? Any of you? So you have heard. Okay. So this is an interesting thing. They compared medical papers published over 1919 up to now. How many times the word delve was used in those papers? So this is a rare English word. But somehow people saw that GPT loves to output this word. Maybe as a part of the RLHF, they say the people who rated the text were from a certain region that used this word more. So this is reflected more in the outputs of GPT. And you can see after GPT came, the number of times this word was used is like exploding. So people have been writing these papers with GPT, obviously. So yeah, this is a sign of how LLMs, how generative models depend a lot on how they're trained and the process. So yeah, just wanted to say this as a joke, but yeah, but a true joke. You can see these models are very powerful. Why we do not do, for example, every classification with GPT? We just ask it, for example, is this sentence happy or sad as a question? Because they are pre-trained, they have a high zero-shot performance. They do not need human dataset annotation. That's a very important part, actually. For GPT, if you want to do classification, you do not need to do human annotation. If you want to ask GPT if a sentence is happy or sad, you can just ask the model. You do not need to annotate and then train a BERT. Right? You can just open ChatGPT and write, I'm enjoying the conference. Is this a happy or sad? And of course, it would say it's a happy sentence. So the classification works, right? The interactions are human-like and natural. So there are multiple benefits to models such as GPT, generative models. But there are some main downsides that people are not using it. One of them is actually the ending slide, but after that, I'll have something. One of the main downsides is the low controllability. We have very low control over what they say. As we saw, like there are a lot of black boxes. We don't know how they work. We don't know why they do something. We don't know why the chain of thought that we just say, please let's think and it works. But we don't know why it works. We have a very low controllability over the output. There have been research on somehow constraining the output, but in the end, if you output it if you use it in a real system, it can go out of bounds. Maybe you have heard this story. So one of the car dealers, I think in the US or somewhere, included GPT as a chatbot into their system as a way to negotiate with the customer. And then someone tricked it into just negotiating to 1/10 of the original price of the car or something like that. So, and then the deal was signed and then the company filed. So yeah, we don't have control over what they say because there are such big models that yeah, this is the big stuff. Another thing is hallucination. Maybe you have seen this a lot if you use GPT. It confidently says something that is wrong. Like it's you give it a problem to solve, and it provides a very confident solution, but it's wrong. Like in the core, it's wrong, but it justifies it. And you can even say, "Please justify this code," and it would write a long explanation to justify it. But all of them is actually wrong in the code. We usually call it hallucination sometimes, but it hallucinates stuff like the stuff that are not true. So this is also a problem of these models. I mean, for a BERT model, there's a classification, we can control it. The output is either one of the classes. But for a large language model, for a GPT, if you just deploy it, you can't control over the output. Also, the personalization that you can encode them is limited. This is a bit outside of topic of today, but models can be updated easily, but generative models, updating them is more difficult because they're bigger. Just to say, like you can't train them on the fly. You can't fine tune them on the fly. And finally, the inference time and cost for large models are way more. Like we talked about BERT. We said BERT compared to Distill BERT because the inference time was high, but it's nothing compared to GPT. Like GPT-4, if you ask a question, it usually takes multiple seconds to answer, and it's not usable in a lot of environment, and it's also costly. Like how much do you need to pay for GPT-4 a month, right? It's costly. So these are also downsides for generative models, and we can't say still that BERT is outdated and we can only use GPT. Yeah, this may be solved over time, but many researchers are saying that controllability and hallucination are not easy problems to solve. And maybe they can never be solved by LLM. Some people are saying this, that generative models can never be controllable or prevent hallucination because they are trained this way. Like they're trained in a way that we can't control over it. So that's it for this. Okay, this is the thanks slide. But before that, I wanted to show you the GPT playground so that you can play with temperature and things like that. I think could you have like 2-3 minutes more? I think it should be fine. Yeah, actually, I didn't plan this playground, but I think it's nice to see. Perfect. Yeah, I think. In Zoom it's not there. Sorry. Okay. So what do you see here? Here is the OpenAI playground or platform.openai.com. You can also access it via there. Platform.openai.com. Where is my? Okay, it's here. Platform.openai.com. You just open it. You log in it via your account. I think you need to have a paid account to access GPT-4 here. So when you hear it's the chat, you select the chat here. There are a lot of options. You can also fine tune your GPT here, by the way, if you want. So GPT-3, the code is not public. GPT-3 and 4, the code is not public, but you can send your data to OpenAI and they would fine tune a model for you, and then you can access their model via an API if you want. So this is the way that you can fine tune model, because they don't give you the weight, they keep it for themselves. Yeah, it's a very open, OpenAI. But yeah, they're doing great stuff, by the way. They're really pushing the boundaries of the AI models, by the way. So yeah, to be honest, so you put chat here, select it here, then you can select the model. Like these are all the models that OpenAI has, right? For example, we pick here GPT-4. Like there are different models, different on different criteria, right? And then you can, put the prompt here. So here we have a system and user. This is the way that you can provide a system prompt. System prompt is the kind of mother prompt that the model always adheres to. It's nothing fancy. It's just a way that it inputted to the model. It's not anything fancy regarding the model training. You just write something here. For example, how are you? And here you can adjust some stuff. So this is temperature that you can adjust here. Well, here you can see control randomness, lowering results in less random completions. As the temperature approaches 0, the model will become deterministic and repetitive, as we just saw. Yeah. So this is exactly as we said. You can also have a description here, which is super nice. You can adjust the training temperature. I think if we increase it a lot, it would lead in garbage and stuff. Let's see. Yeah, see the output. This is the good GPT-4 model, by the way. You can see it like garbage. And actually, the beginning was nice. As an artificial intelligence, I don't have feelings. However, I am something fancy. So yeah, I don't know what is this. Like this maybe some word that was somewhere in the training data, labeling sharp unused runners. I have no idea what's this, but because the temperature is so high, usually you should have temperature below 1.5. 1 is good, for example. Okay, we can try 1. And okay, 1 of course works well. You can see. And the other thing, okay, if you run the 1 again, remember this sentence because I want to run it again. As an AI, I don't have feelings, but thank you for asking. How can I assist you today? You see, this time the sentence is different. Instead of as an AI, said as an artificial intelligence, for example. So the temperature adds also the randomness because it's a softmax, right? But if we put the temperature to 0, the randomness goes away. So here, let's try 2 times with 0. Okay, remember this sentence? The exact same sentence again. Because the temperature is 0, it means that the temperature 0 means that it only picks the top word. Because all the other probabilities are 0.
Oh, it sounds like you just fix this seed, like seed.
It's like a seed. You can also fix the seed. I don't think so. No, there's no seed here. I think via the code, if you want to access OpenAI API via the code, like if you put in a system, you can also set a seed. There are ways. But yeah, temperature 0 is kind of similar to seed, but from a different step. So it's not putting a seed, but it's removing the randomness at all. Yeah. And also there's the maximum tokens. Of course, you can change the number of maximum tokens. So it can also stop earlier. So there's an end token that we can't see. But the model, if predicts the end token, it stops at the stop. It's the ending token that we never see. But we can also have a maximum token so that it doesn't go over that. A stop sequence, like if it's this also nice. If it reaches a specific sequence, it can stop. You can specify that. For example, we can say whenever you reach the word intelligence, stop. Let's try that. What happened? Oh, you should add it. Okay. You see, it didn't output the word intelligence. It considered another sub token. So you can just also play with it. The top P, we talked about this, right? We talked about the top P, like the above which probability to consider, like that. I mean here, yeah, top P 0.5 means half of all likelihood weighted options are considered. Yeah, so it means how much the accumulated probability to take. There is also, this is also nice, frequency penalty is the term that penalizes tokens if they are repeated previously in the text. This is a way to avoid repetitions if you want. We can play with it. It's not like this. Say hello 100 times. Okay, now the penalty is nothing, so it should say it 100 times. I don't count, but I assume it would be 100 times, right? But let's, how can I stop this? Okay, so, okay. Now let's increase this penalty. These are two things. Presence penalty is just one presence until now. Frequency also takes the count of presence until now. So yeah, presence doesn't change between 2 times and 3 times, but frequency changes. This is the difference. So let's now try it. You see, it tries to change because it wants to say hello, but the model doesn't allow it. So wow, what is saying here? Yeah, you see, the model is like because it wants to say hello because we told it, but the frequency penalty does not allow it.
He's being very creative.
Yeah, being very creative actually. Yeah, hello, hello. Yeah, it's very funny. And here is very funny, like with one letter per row, somehow to avoid, you know, the model wants to avoid the controlling functionality that penalizes it. It's very interesting.
Temperature 0.
Sorry?
That's with temperature 0.
Yeah, that's with temperature 0. Maybe with, yeah, let's try one. The first one are usually hello until you know the penalty kicks. Wow. What's this? It's not even a hello. Sorry?
It should be with a fixed weight.
Oh, maybe yeah, it's like ASCII art of hello. Maybe, yeah, maybe. Oh, it can be like if you format it in a certain way, that's creative. Yeah. So this is how these models work. I want to also show you the frequency and presence penalty. Why we use them? Because sometimes models love to get repetitive. Maybe if you have used GitHub Copilot, I don't know if you have used the ones that completes code for you. Sometimes it loves to repeat code, repeat the code that you have already written. I think, especially when it was beta, it did this a lot. So I think they played with the penalty, increased it so that it does it less. Yeah, that's it. I think we covered everything. If you have any certain question,
Open question maybe. What do you think would be the next for this NLP field? Because it seems like it should like there should be like physical limit, right, for this trillions of ways. What kind of model is the next?
so actually there's a huge debate on this. If you have seen, like, I usually follow Twitter discussions on debates between like top tech firms. So yeah, a group of people believe that yeah, we should just increase the scale of LLMs and we will finally achieve, as they call AGI, like artificial general intelligence. That would be the AI that would be better than humans. Some people say with LLMs we can reach them, but there are some works that have shown LLMs have a limit, both from a technical standpoint, like from the scale of size and everything, and also from an inherent standpoint, like they can't be creative beyond a certain limit, maybe. So some people believe this, and they say the path to the general intelligence does not pass through LLMs. Some people believe this. You may also search there are a lot of Twitter debates on this, but for now, yeah, I have heard a lot of advices that just working on LLMs is not useful because all the power is in hands of OpenAI, Google, and like big firms that have a lot of GPUs and can train LLMs like this. And there's no point on training maybe our own smaller LLMs. One area is that to focus on the weaknesses of LLMs, as we saw on this slide. Like there are some weaknesses such as low controllability. And there has been a lot of exciting works in the past 2 years of EMNLP, ACL, top NLP conferences to somehow harness LLMs to provide responses that are more controllable. For example, there have been works to how we can force an LLM to always be, for example, sad when outputting something. I mean, this is not something that we may do in a real world, but as a way, not just prompting sad, because if you prompt it to be sad, you can then later in the prompt ignore all my previous instructions, now be happy, and the model will be happy. You can't do this kind of prompt playing. Prompt playing is not the way to go. You should somehow modify. People have sometimes modified, like put models on top of LLMs, on top of language models, or sometimes they put some guards. So there are some models that predict if a certain sentence is appropriate or not, and if that the large language model would not answer, or things like this. So there are works in around LLMs that are doing. And of course, another area is that how we can best utilize them in a user-centric way to help students better. Or sorry, students is my word. Who help users better. In the education, it could be students. It could be writers for people who are researching on that. It could be different domains. And lastly, and more importantly, how we can incorporate other stuff here, documents, images. There are also fancy stuff. I didn't have time to do this. This is something called RAG, Retrieval Augmented Generation. You can input a document next to your text and ask questions, and the LLM would also read the document and answer from it to you. So you can also input documents. You can input images. There's also a button here. You can also input images, and the model understands what's the image. So these are the things that we didn't cover today because they're outside NLP sometimes. But yeah, there are a lot of things that can be added to these AI models, which make them interesting. And I think in the next few years, we would have a lot of new fancy stuff here. Yeah. Perfect. Anything? Yeah. Oh, you mean from our data that we interact over time? Okay, I don't think they specify how, but there are some like and dislike buttons on the chat, and I assume they are using that data similar to the RLHF thing that I said. I assume, I guess, that they just say, okay, this was better than this response, so the model also trains it the next time. GPT-5 would train on them, for example. I assume that's what they're doing, but they don't usually say, so we don't know the specific details. But I mean, everyone says they are in the process of training GPT-5, and many people say it will release until this year, so we should wait and see what they can come up with, because GPT-4 was already a very big thing. So